My dear students, we studied the ray theory of light in the previous class. According to this theory, the energy of light follows narrow paths called rays. These rays follow some principles, and we studied the principles followed by these rays as well. We talked about the Snell's law of reflection under this topic. Today we are going to study the construction of the spherical lens and the application of the spherical lens in fiber optic communication. There are many applications of spherical lens in fiber optic communication. So let us study the construction of the spherical lens first. Spherical lenses are made of two spherical surfaces as shown in this diagram. The radius of the spherical surface on the left side in this diagram is R2, and the radius of the spherical surface on the right side of this diagram is R1. So R1 and R2 are the radii of these two spherical surfaces, and this is the structure of the spherical lens. The line which passes through the center of the spherical lens is known as axis. So we can see the axis of the spherical lens in this diagram. Focal points are located on either side of the spherical lens. There is a focal point on the left side of the spherical lens, and there is a focal point on the right side of the spherical lens, and we will represent the focal point by capital FP in this lecture. So FP will represent the focal point. So there are two focal points of the spherical lens. One is located on the x-axis on the left side of the spherical lens, and the other one is located on the axis as well, and it is on the right side of the spherical lens. The plane which passes through the focal point and is normal to the axis of the lens is known as focal plane. So we can see two focal planes in this diagram. One focal plane on the left side of the spherical lens and the other focal plane on the right side of the spherical lens. So the focal plane is normal to the axis of the lens, and it passes through the focal point. Let us talk about the focal length, which is a very important parameter of the spherical lens. The distance between the center of the spherical lens and the focal point is known as focal length. This focal length is represented by small f. We want to find out the relationship between the focal length of a spherical lens and its different parameters. We consider equation number 1. We can find out the focal length of a spherical lens with the help of equation number 1, which is 1 over f is equal to n minus 1 into 1 over r1 plus 1 over r2, where f in equation number 1 represents the focal length of the spherical lens, n represents the refractive index of the material of the spherical lens, and spherical lens is made of glass. And we know the refractive index of the glass. The refractive index of the glass is 1.5. R1 is the curvature of one spherical surface of the spherical lens, and R2 is the curvature or the radius of the other spherical surface. So if we want to find out the focal length of a spherical lens, we can do it with the help of equation number 1. Let us find out the relationship between the focal length and the diameter of a spherical lens. Keep it in your mind that the diameter of a spherical lens is represented by capital D. So in order to find out the relationship between the focal length and the diameter of a spherical lens, we assume that the spherical lens is in the form of a sphere of diameter d. If it is in the form of a sphere, then R1 will be equal to R2, and it will be equal to R, where R will be the radius of this sphere, and this R will be equal to d by 2. So equation number 1 can be written as 1 over f is equal to n minus 1 into 1 over r plus 1 over r. So basically we replace R1 and R2 in equation number 1 by capital R. If we simplify this equation, we get 1 over f, which is equal to n minus 1 into 2 by r. We put the value of r in this equation and we get 1 over f, which is equal to n minus 1 into 4 by d. And what we do now, we put the value of n in the second equation. If we put the value of n is 1.5 because the spherical lens is made of glass. So we get 1 over f, which is equal to 0.5 into 4 by d. So 1 over f will be equal to 2 by d and f will be equal to 0.5 d. This is a very important relationship between the focal length of a spherical lens and its diameter. This relationship shows, this equation shows that focal length of a spherical lens is directly proportional to its diameter. So if we want to change the focal length of a spherical lens, we need to change the diameter of the lens. A spherical lens having large focal length will have a large diameter, and a spherical lens with small focal length will have a small diameter. So if we want to design a lens of small diameter, we need to keep its diameter small. And this is the minimum possible focal length of the spherical lens, which is given by 0.5 D. Now we talk about the functions of the spherical lens. If we look at the diagram, a collimated beam of light is given. What is a collimated beam of light? All the rays of a collimated beam of light are parallel to one another. So if we want to focus a collimated beam of light to a single point, we can do it with the help of a spherical lens. An incident collimated beam of light is focused to the focal point by the spherical lens. So the spherical lens is used to focus all the rays of a collimated beam of light to the focal point. If this collimated beam of light makes an angle with respect to axis, then this collimated beam of light is focused to a point in the focal plane. And this point is located in the focal plane. Now let us talk about, some principles. The light ray which passes through the center of the spherical lens does not change its direction. The central ray does not change its direction at all. So this is principle number 1. Principle number 1 states that ray traveling through the center of the lens is undeviated. The direction of the central ray does not change. Incident ray traveling parallel to the axis is focused to the focal point. If we look at this diagram, the incident ray is parallel to the axis of the spherical lens, and the transmitted ray is focused to the focal point. So if a ray travels parallel to the axis of the lens, this ray will be focused to the focal point, and this is principle number 2. Let us consider principle number 3 in this diagram. You guys can see the central ray in this diagram, the ray which passes through the center, and we know that the ray that passes through the center is undeviated. This ray does not change its direction. We consider another incident ray. The incident ray which is parallel to the central ray. So an incident ray which travels parallel to the central ray intersects the central ray in the focal plane after transmission through the lens. This incident ray will be focused to a point in the focal plane, and this point is given to you guys by the intersection of the central ray and the focal plane. Principle number 4. An incident ray passing through the focal point travels parallel to the lens axis after it emerges from the lens. So let's say we have got the source on the focal point. And the source radiates a light ray which travels towards the spherical lens as shown in the figure. This incident ray is made parallel to the axis of the spherical lens. If an incident ray emerges from the left side of the focal point, you guys can see this diagram, the incident ray emerges from the left side of the focal point. This ray will intersect the axis of the spherical lens on the right side of the focal point. So the incident ray emerges from the left side of the focal point, and the transmitted ray intersect the axis of the spherical lens on the right side of the focal point. This is another principle. This is another important principle. We will use this principle in the upcoming lecture. The spherical lens can collimate a beam of light which emerges from the focal point. It means if the source is located at the focal point, then the transmitted rays travel parallel to the axis. And these parallel rays are known as collimated beam of light. If we consider figure number 2.8, the source in this figure is located at the focal point. And we know that the source radiates the energy in the form of a cone. So all the rays of the source radiation cone will be converted to a collimated beam of light by the spherical lens. If the source is located elsewhere in the focal plane, then the transmitted rays travel in the direction of the central ray, and we know that the central ray does not change its direction. We consider figure 2.9. You see, in figure number 2.9, the source is not located at the focal point. The source is located in the focal plane. This source radiates the energy in the form of a cone, and all these rays will be converted to a collimated beam of light. And all the rays of the collimated beam of light will be in the direction of the central ray, because the central ray does not change its direction at all. This ray is undeviated. The central ray is undeviated. It does not change its direction. So we discussed the spherical lens. Let us discuss another lens which is known as graded index rod lens. This lens is simply known as green lens. Green rod lens is applied to fiber optic communication in a number of ways. The gloss rod is made in such a way that its refractive index decreases with respect to axis. So this is the graded index rod. You guys can see the axis of the rod. N1 is the refractive index of the first cylindrical layer. N2 is the refractive index of the second cylindrical layer. N3 is the refractive index of the third cylindrical layers. And N4 is the refractive index of the fourth cylindrical layer. And you see N1 is greater than N2. N2 is greater than N3. And N3 is greater than N4. The refractive index of these layers decrease with respect to the axis of the rod. The light ray follows a sinusoidal path in the rod. If the light travels in this rod, it follows a sinusoidal path as shown in this diagram. So the light in the graded index rod travels sinusoidally. The distance traveled by one complete cycle of the light is known as pitch, and pitch is represented by capital P. If we cut P by 4 portion of the green rod, then it becomes a lens. This lens can collimate a beam of light emerging from the center of the lens. You see, the source is located at the center of the lens. It radiates, the source radiates the energy in the form of a cone. The central ray will not change its direction. All the remaining rays of the cone will follow a sinusoidal path, and all these rays will be converted to a collimated beam of light by the green rod lens. Similarly, this lens is used to focus the collimated beam of light to its central point. So we studied the construction of the spherical lens. We studied the mathematical equation which is used to find out the focal length of the spherical lens. The different principles followed by the rays when they pass through the spherical lens. And we discussed the construction of the green rod lens in this class. Thank you so much.